Good afternoon, everyone. I once again warmly welcome all the participants back after the lunch break. Let us continue our learning journey with the same enthusiasm and zeal. As we look for sustainable solutions to modern infrastructure challenges, today's session addresses a vital intersection of these domains. To guide us through this critical subject, we have a distinct honor of hosting a highly accomplished academician, researcher, and institutional resource person, respected Dr. Rajendra Prasad Verma sir. Dr. Verma currently shapes the academic landscape as the Dean of Academics and Administration, Associate Professor, and Head of the Civil Engineering Department at GGSE STC, Bokaro, Jharkhand. With nearly a decade of dedicated teaching experience and over 4 years of core doctoral research, his insights beautifully bridge deep theoretical framework with institutional excellence. Academically, Dr. Verma earned his PhD in civil engineering in 2021, specializing in the application of computational fluid dynamic of structural wind forces. He holds a Master of Technology in Transportation Engineering, where his pioneering project focuses on advanced pavement design using geotextiles. Complementing his rich academic tenure, his past industry experience includes serving as a structural engineer managing major bridge and culvert construction for the Ranchi Ring Road project. As an active researcher and recognized PhD supervisor under the Jharkhand University of Technology, Dr. Verma has authored over 10 high impact research papers in prestigious national, international, and UGC CARE approved journals. What makes his presence incredibly fitting for our FDP today is his extensive published research directly aligned with our theme. He has conducted deep dive studies on the compaction behavior of muram and soil mixed with fly ash, cement strength improvement using marble dust, and partial replacement materials utilizing stone dust. Furthermore, his published work on dam induced risk analysis highlights his expertise on geotechnical risk assessment. Beyond research, his technical acumen is utilized as a civic scale. He serves as an expert review committee member for water hardness treatment plants in mining affected areas. He is also a life member of the Indian Society of Technical Education and the International Association of Engineers. Today, Dr. Verma will be sharing his valuable expertise on a topic that sits perfectly at the heart of our FDP theme: ground improvement technique using waste materials. This lecture promises to give us practical, eco friendly engineering methods to transform industrial byproducts into high utility geotechnical assets. We are incredibly fortunate to have such a versatile expert and session researcher to ignite our learning today. Everybody, please join me in welcoming our distinguished speaker, Dr. Rajendra Prasad Verma, sir. Sir, we welcome you.
Thank you, ma'am. Good afternoon, everyone. I am audible.
Yes, sir, you
I
are
am
audible. Kindly proceed.
okay. Thank you, sir. I am Dr. Rajendra Prasad Verma from Civil Engineering Department of Guru Gobind Singh Educational Society Technical Campus. Today, I am presenting on the topic ground improvement technique using waste material under the ISTE BNY Knowledge Enhancement Program 2026. This presentation focus on the use of waste material, especially plastic waste, in improving soil property for sustainable and economical construction practices. This slide explains the major objective of ground improvement techniques. The main purpose of ground improvement technique is to improve weak soil so that it can safely support foundation and construction activity. The objective include increasing shear strength, stiffness, durability, and stability of soil. It also helps in reduce under undesirable property such as shrinkage, swelling, compressibility, and liquefaction. Another important objective is controlling permeability and ground flow through the soil. Therefore, ground improvement method provide effective engineering solution for problematic soil condition. Classifications, that means ground improvement technique, are broadly classified into four major categories. These include mechanical modification, hydraulic modification, physical and chemical modification, and modification by inclusion of confinement. Each group offers a specific chemical or mechanical interventions to solve distinct subsoil challenges. When we integrate waste material into this technique, our objective expand into environmental sustainability. We provide alternative disposal solution for plastic waste, achieve economical soil stabilization by determining optimum plastic fiber content and minimize the industrial carbon footprint. Mechanically, this includes successfully increase the shear and textile tensile strength of the soil matrix while decreasing its overall compressibility. Several landmark studies support this approach. Hunter Hall in 2004 demonstrate enhanced tensile strength by curing out plastic waste. Fiber is unconfined compression test. Hacker and Sol in 2013 used plastic waste bottle pieces in model plate load test to determine a 2014 detail the definitive positive impact of HDPE plastic waste on the unconfined compression strength of soil. To evaluate this soil mixture, we really on established testing methodology, starting with the triaxial test. This test measures shear strength under control, saturation, confining stress, and vertical axis stress. Depending on the drain conditions of our project layout, we perform unconsolidated drain, consolidated drain, or consolidated drain test. Next, the direct shear test. Utilize a standard shear box. Apparatus allow us to determine the primary shear parameter. It helps evaluate the cohesion and internal friction angle of both cohesion and non-cohesive soil at predefined densities and moisture content, specifically under consolidated drainage conditions. This flowchart represents our optimization methodology. We systematically add increasing percentage of plastic strip to the soil, execute direct shear or triaxial test, and monitor the resulting bearing and shearing strength. We map how cohesion and the friction angle change. Containing this incremental addition until the bearing capacity reach a peak and begin to the decrease. Our expected outcome follows a clear curve where the bearing capacity values increase up to a specific threshold before beginning to decline. This peak marks the absolute optimum content for utilized waste plastic in that particular soil type, providing us with the exact design parameter for ultimate bearing and shearing capacity. Shifting focus to the classical mechanical modification, let us define the compaction. It is the simplest ground improvement technique where soil is defined mechanically through an external compactive effort by explaining air void through the application of energy and control moisture. We pick the soil particle close together. The operational benefit of the compaction are extensive. It increases shear strength, reduce compressibility, limit permeability, mitigate liquefaction potential, and control swelling and shrinkage to prolong durability. To execute this effectively, we must strictly specify placement conditions like water content and layer depth. Select proper equipment like roller, compactor, and implement statically controlled testing. In the laboratory, we established our baseline using a standard compaction test to obtain a proper compaction curve. This defines the optimum water content and maximum dry density. We contrast the standard Proctor test, which use three layer of and 2.7 kg ramble with a 300 drop. Again, the modified Proctor test, which apply a higher compactive effort using 5 layer and a 4.9 kg ramble with a 450 drop inside a 1000 mold. Then performing shallow surface compaction, field engineer must closely regulate operating frequency, the depth of soil layer, and the number of roller passes. Especially care must also be taken during the freezing temperature. As shown in the graph, dry densities increase rapidly over the first few passes of a roller before flattening out, indicating dimensional return. The compaction curve illustrates with the happens to the three phases of soil, air, water, and solid. Soil particle as water is introduced, water initially acts as a lubricant, allowing particle to reorient into a denser configuration. This ends the lowest void ratio and highest dry density at the optimum water content, beyond which water being to displace soil solid. Zero air void curve corresponding to a theoretical state of 100% saturation, where all air is entirely expelled because achieving a saturation level greater than 100% is physically impossible. This curve serves as a mathematical boundary line. In practice, all valid laboratory compaction point must plot strictly to the left of the zero air void curve. Compaction fundamentally alter clay fabric microstructure, compacting soil on the dry side of optimum result in a random liquid fabric. However, applying a higher water content or an increased compactive effort shift the orientation into a highly parallel, more dispersed fabric layout, directly altering the soil engineering behavior. This graphic tracks dry density versus moisture content alongside the theoretical saturation line. It clearly shows the curve reaching its vertex at the maximum dry density point. Notice how the curve naturally parallel the 100% saturation, zero air void curve, and the 80% saturation line as a moisture content increase beyond the optimum level. For shallow application, equipment is categorized by delivering mechanism. A static roller include a smooth steel roller, pneumatic rubber tire roller, grid roller, and seafoot roller, which are highly effective for cohesive soil. For impact and vibratory action, we utilize temper, ramble, plate, compactor, vibrating roller, and high energy impact roller. This slide illustrates the diverse configurations of cello compactor used in the field, ranging from a small hand guided ramper and walk behind plastic compactor to heavy tools, ship foods units, self-propel, a smooth drum, vibratory roller, and non-circular impact compactor. When compacting sand density varies significantly with depth. If we compact a single thick layer or leaf, the top and bottom exhibit lower relative density compared to the middle section. To achieve uniform relative density throughout the entire depth, the construction strategy must rely on compacting several thin successive leaps sequentially. Compaction control is a systematic quality assurance excessive field specification mandate testing at regular intervals, such as talking on field test for every 1,000 cubic meter of the compacted soil. We measure the field dry density and actual water content using traditional sand cone method or automatic nuclear density meters to verify compliance with the project design criteria. Compacted soil can experience sharp volume change under load when exposed to moisture. This consolidation test data highlight collapse settlement which occur when a unsaturated compacted soil is loaded and subsequently saturated with water. The sudden softening of the soil structure causes rapid surf settlement, which must be carefully accounted for in design calculation. When loose in situ soil extend to large depth, surface compaction is insufficient to meet loading and environmental performance criteria. In this scenario, we must resort to deep soil improvement strategy. These are broadly divided into deep ground improvement techniques, deep ground reinforcement technique, and a specialized deep ground treatment. One of the most prominent deep improvement methods is dynamic compaction. This technique involves rapidly dropping a massive heavy weight from a crane directly onto the ground surface. The pounding weight range from 6 to 172 ton and they are dropped from the typical free fall height varying between 10 meter to 40 meters. The degree of densification achieved is directly proportional to the total energy input, which is a function of temper mass and drop height. It is also heavily influenced by the soil saturation level, fine content, and permeabilities. For instance, a standard 6 to 30 ton weight can successfully densify loose sand to a maximum depth of 3 meter to 12 meter. Dynamic compaction is never random. It is executed systematically in distinct phase across rectangular or triangular grid pattern. Each overall project phase consists consider of multiple phase labeled as primary, secondary, and tertiary phase. This slide shows a typical 18 by 18 meter grid where primary and secondary impact location are clearly demarcated to ensure uniform coverage. The spacing between impact points depend on the depth of the compressible layer, soil permeabilities, and the locations of the groundwater level. As a fundamental rule, deeper soil layer require wider grid spacing with higher energy concentrations, whereas the shallow upper layer are compacted later using closer grid spacing and lower height. The repetitively heavy impact create drop across the side. The creator are systematically backfill with sand and granular material after each tempting pass to maintain a level working platform and introduce high quality material into the ground because the soil void collapse vertically. The lateral ground have around this crater is generally very small. The physics of dynamics compaction relies on wave propagation. The impact energy is transferred through the soil by two primary wave families. Roughly 67% of the total energy propagated as Rayleigh surface wave, while the remaining volume energy traveled deeper into the ground as a shear wave at 26% and the compression wave at 7%. In a saturated soil, the densification process occur in a stage initial compaction, compress, teeny entrap, micro bubbles, repeated impact cause a temporary increase in pore water pressure, leading to localized microfusing of the soil. This dramatic increase in local permeability allows for the rapid dissipation of pore pressure, followed over time by thixotropic strength recoveries. According to the Lucas soil classification for dynamic compaction, soil are divided into three distinct zones based on the grain size. Zone 1 consists of previous clean granular soil with a plasticity index of 0, which yield the best result. Zone 2 represents semi-pervious soil where multiple compaction phases are required to allow pore pressure to dissipate. Zone 3 comprise impervious clay and silt, which are the worst suited and often required alternative technique. Dynamic compaction is primarily used to compact extensive granular fill. It is uniquely effective for compacting rock fill below water level for boundaries soil where traditional vibratory method struggle or fall. Furthermore, it has become a premier method for upgrading variable waste dump, sanitary landfill, and loose mine waste. In a sanitary landfill, long-term settlement occurs due to void compression and organic decay. Deep dynamic compaction effectively collapse these voids, reducing both immediately and long-term subsidence. In recent field, it increased until wet and drive out oxygen, slowing down ongoing decomposition. In older, completely decomposed fields, it maximizes unit weight to create a stable platform. This systematic visualizing summarize a deep dynamic compaction crane operation. It demonstrates how the energy wave radiates downward and upward from the temple footprint, creating a dense ball of improved soil capable of supporting high bearing capacity, a structure, a structural foundations. For engineering design, Paul and Rodriguez suggest a geometrical approach. They model the individual compaction zone as an approximate ball set defined by a radius A and a depth B. By evaluating this geometric dimension against the instant grid, spacing as engineering can calculate the exact coverage and overlap required for uniform densification. This slide represents the empirical design chart plotting the normalized dimension a small a by capital D and a small b by capital D against the total energy applied per unit area. By calculating our specific damping energy parameter, this calibrate curve allow us to accurately predict the radius and depth of the compacted zone during the design phase. To verify the success of dynamic compaction, we conduct extensive pre-treatment and post-treatment field tests. These case studies overlays show a standard penetration test N values, cold penetration test, deep resistance, and pressure meter test result. Notice the substantial increase in soil property after applying 1.2 and 2.4 megajoule per square meter of energy, validating the depth of improvement. Advanced in situ verification often utilize a self-boring pressure meter. This instrument extends a cylindrical membrane inside the borehole without disturbing the surrounding soil wall. The resulting pressure versus cavity strain curve give us direct high accuracy field measurement of the soil shear module and horizontal stress state. We also rely heavily on non-destructive geophysical testing, including shear wave velocity test and flat diameter test by using an impulse source at the surface and recording wave arrive via downhole geophone. We can preciously map how the mechanical stiffness of the soil change across different depths. This profile illustrates actual shear wave velocity data recorded before and after deep compaction. The baseline curve on the left shows low velocity in this loose soil state. Following deep compaction, the velocity profile shifts significantly to the right, proving an immediate, measurable increase in the shear module and a structural stiffness of the ground down to the 6 meter. Let us look at a major international case studies. The nice extensive in France, two new 3,200-meter runway were constructed on 200 hectares of reclaimed land, considering of loose fill and soft sandy silt. Over 20 million cube meter of fill were placed to prevent dangerous excess pore water pressure. Heavy dynamic compaction was executed in successive phases saturated by precious resting period. Monitor continuous via field CPT and PMT device. The aerial views capture these specialized heavy equipment configurations utilized at the NICE airport project. You can clearly see large scale camping grid and the resulting craters running parallel to the shoreline. Showcase the industrial scale of this ground engineering operation. Our final case studies focus on the TCL fertilizer complex in Babarala, Uttar Pradesh. The site profile considered of highly liquefiable loose fine sand extending down 10 to 12 meters with a very low initial allowable net bearing capacity of just 60 kilopascal. A seismic risk assessment indicates that a magnitude 6.4 earthquake with a peak acceleration of 0.2 gram would induce serve liquefaction across the site. As educators, we also emphasize the importance of pilot testing and proper planning to our students. The engineering team at Babrala did exactly that. This layout show the systematic demarcation of sub-area level from area B1 and B2 up to E1, C3 and D2. However, before subjecting the entire industrial footprint to high energy impact, they isolate two distinct test control pits measuring 30 by 30 meter each. This allows them to preciously calibrate and dynamic compaction parameters and verifying the soil real-time response before full mobilization. How did they measure success? They use a standard field verification method, a standard penetration testing, and cone penetration testing. Let us look at figure which map the SPTN value against depth for the test patch B. The curve with a square mark show the baseline condition before compaction where N values barely scratch past 5 blows per 30 centimeter in the upper zone. Following dynamic compaction denoted by the triangular mark, you can see an immediate spike in soil resistance. Crucially, for our research discussion on food water pressure, dispatch look at the star mark curve taken 1 month later. It clearly demonstrates the phenomena of soil strength again over time due to thixotropy and delay consolidation as excess pore pressure fully equalized. Based on those trial outcome, the engineer's specification were fine-tuned to hit two rigid milestone, first achieving a safe allowable bearing pressure of 200 kilopascal at a depth of 2 meters, and second is ensure a zero liquefaction state during the design earthquake. To achieve this a heavy duty 4-pass dynamic treatment program was enacted. Phase 1 and 2 utilized 10-ton hammer drop from a massive height of 16 meters, with the second pass arranged in a standard grid to fill the gap of the first. Pass 3 intensified the energy deployed a 15-ton hammer from 16 meters to target the deepest position of the loose set. Finally, pass 4 act as a ionic pass to densify the distant superficial soil using a 5-ton hammer from 16 meter on a tight 2.5 by 2.5 meter grid. In massive civil project, excuse in only as a good quality monitoring framework and Barbala the primary metric for ensure against liquefaction was past treatment. The entire site was selected into the sub areas we saw earlier. If we look the specific plot for the areas to verify that the treatment was uniform across the entire facilities, monitoring was extended across all blocks. Figure 4 detail area B and figure 5 cover area C. Notice how both charts reflect the exact same pattern. A dramatic shift of the SPT curve to the right, even at depth of 5 to 10 meters, where loose sand previously threatened a structural collapse under seismic load. The refined soil skeleton considering and high and value well above the minimized safety threshold. To conclude this first case study, the dynamic compaction program achieved an overwhelming success. It successfully densified loose granular sand layer all the way down to a depth of 12.5 meters. Looking at the engineering matrix, the soil load bearing capacity experienced a more than threshold increase, skyrocketing from the initial 60 kilopascal to a robust 200 kilopascal. Most important, the entire industrial side was effectively earthquake proof against its design seismic risk, validating dynamic compaction as an economical alternative to deep piling in granular deposition. Next. Now, let us pivot from loose granular sand to a different soil challenge, soft clay and silty matrix as we now pure vibrations or impact compaction fail in cohesive soil because water cannot escape quickly inside. We use a stone column developed globally through methodology like the Japanese vibro-composite system or European vibro flotation technique. These columns are constructed by compacting a stone aggregate in zero point 0.4 to 1 meter deep layer. This can involve casing, driving, or a specialized deep pouring. In unique scenario, mortar injection is used to form rigid column. Typically, this column range from zero point 0.6 to 1 meter in diameter, can extend up to 20 meter deep and use crushed rock size between 20 to 75 mm arranged in a square or triangular pattern, a space at 1.5 to 3.5 meter. Why are a stone column too effective in soil clay? They perform a dual function, reinforcement and drainage. Structurally, because the stone column possesses a much higher stiffness and shear modulus than the surrounding weak clay, a large percentage of the surface load is directly transferred to the stone column. They mimic dig pile foundation but drastically reduce cost because they do not require a structural pile cap or rigid connection. Hydraulically, they act as vertical sand gravel drain by reducing the drainage path distance. They accelerate pore water dispatch completely long-term settlement in week instead of year. A point 2, a point 3 meter granular sand blanket is laid at the surface to serve as both a drainage path and a stress distribution layer. For our research student, understanding failure mechanism is wide, vital for safe design. Indian Standard Code highlight three principal failure modes for a single column in a homogeneous soft layer. Figure 2A show a long stone column with firm or floating support. It fell via bulging, typically occurring with an upper zone of 2 to 3 column diameter where lateral confining pressure from the weak soil is lowest. Figure 2b display a short column. Figure 2b display a short column resting on a rigid base which fell due to lateral shear. Figure 2c show a short floating column which undergoes punching failure directly into the weak subgrade benefit is. When we deal with complex, non-homogeneous, stratified profile, the failure mechanism change as classified in figure 1b. If a soft layer side right at the surface, we see a combination of sharp bulging and shallow shear failure. If there is a thin, ultra soft layer embedded deep down, it creates a highly contained localized bulk. However, if that ultra soft clay or ongoing layer is thick, a massive localized bulging failure occurs. Within that specific weak boundaries, this underscored why detailed site investigation is mandatory before estimating column confinement. To translate this complex analytical formula into practice, we train our engineers on a specialized numerical tools like a stone C column software. The design workflow consists of 5 clear steps. Step 1 required entering the stone column grid layout such as rectangular grid with 1.5 meter spacing and the foundation geometry. Second step is capture the column material property such as the friction angle, which is typically set around 40 degree, and the dry unit weight. Step 3 involves inputting the stratified soil layer, including depth boundaries, constant modulus, cohesion, and Poisson's ratio. Step 4 load the comprehensive project data, and step 5 generate the structural output and settlement reduction curve, often computing using preable analytical diagram. Let us now compare traditional stone column with a highly efficient variation RAM aggregate pier. This step-by-step field construction is very elegant. First, a cavity is drilled using a mechanical agar, and temporary casing is installed. If cave-in are a risk, second, a high-quality crust, a stone layer is placed at the bottom of the open cavity. Third, a patent believed temper ram this bottom stone layer forcefully, driving the aggregate laterally into the surrounding matrix to produce an enlarged high capacity ball. Fourth, successive aggregate layer are densified in thin lift of 30 centimeter using the high energy temper. Finally, the top of the compacted pier is preloaded, ensure the incredible steep column. This matrix outlines the critical engineering trade off between a stone column and aggregate pier. Traditional stone columns are built for depth, spanning 5 to 15 meters with a typical wide spacing of 4 times the diameter 4D, and thick lip fill is 1.5 to 3 meter. This held an allowable foundation pressure of 25 to 150 kilopascal. Conversely, aggregate pier are shorter, high intensity, inclusive spanning 2 to 8 meters with a tight spacing of 2D because they are compacted in ultra thin lift of 20 to 30 centimeters using a backhaul with a specialized temper. Let us dive deeper into the overreaching family of deep vibratory method being with vibro compaction. This technique uses depth directed horizontal vibration to compact loose soil formation across massive depth. The radial zone of compaction achieved around a single pop is directly determined by the mechanical characteristics of the vibrator or float. However, the primary factor determine whether this technique will succeed is in the grand distributions of both the in situ soil and input backfill material. This grain size analyze distribution chart serve as a golden rule for choosing a deep compaction method. The x-axis represents the grain diameter from fine clay up to coarse clay, up to coarse gravel, while the y-axis show the percentage passing. The chart is divided into four distinct operational envelopes labeled John A through John D. Let us break down exactly what this John means for the engineering design. Okay, as a classified by standard geotechnical practices, soil filling within Zone A and Zone B consists of clean gravel and coarse sand. These soil can be easily compacted using deep vibratory vibrocompaction, also known as vibrofloat, because they rearrange radially under horizontal shear wave. However, soil in zone C and zone D cannot be densified by the vibration alone. Zone C soil represent fine silt sand that are highly susceptible to earthquake liquefaction. This required the physical installation of a stone column to achieve stability. Zone D soil contain high clay friction. They are completely uncompactable by vibration but can be reinforced, stiffened, and rapidly drained by inserting a stone column. Technologically true vibroflotation relies on a specialized depth probe that generates a pure horizontal motion from an internal eccentric vibrator. Trying to use a standard top pile driving vibrator operating in a vertical mode is highly insufficient for shifting lateral soil grain. Modern techniques can even match the operating frequency of the probe to the natural resonant frequency of the soil skeleton as seen in the Miller resonant compaction technique. On the other side, vibration, vibro replacement use identical mechanical rigs but introduce high pressure water or air as a jetting medium to flash out weak material, backfilling the void with graded stone aggregate. To reiterate, the primary objective of hybrid compaction is the deep densification of clean coarse gravel soil containing less than 10% to 15% silt. The physics are a straightforward cohesionless soil particle possess no intermolecular bond. When subject to intense depth vibrations, their temporary interlocking structure collapse as shown in the before and after graphics. The loose particle rearranged into an optimal closed peak configurations which significantly reduce the soil overhead or void ratios. In the field, process follow three distinct visual phases. First is penetration. The heavy hydroprop is lower using water jetting and horizontal vibration to easily liquefy the soil directly beneath its tip, letting it sink to the target depth. Second is compaction. The water flow is restricted and the intense horizontal vibration force the surrounding sand grain into a dense state, creating a cone of depression around the probe. Third is backfill. Granular sand or gravel aggregate is fed from the surface to fill the crater as the probe is slowly extracted in a state, leaving behind a highly dense column of compacted ground. To summarize its parameters, hydro compaction applies strictly to coarse soil with low fine. Its primary benefit include increased shear strength, enhanced elastic stiffness, and a total reduction in a liquefaction potential. It is heavily used in both onshore and offshore environments for heavy structures like chemical plant, storage tank, airport runway, and port wall. Embankment, remarkable modern heavy vibrator can achieve a maximum treatment depth of up to 60 meters. When dealing with soft silt, plastic clay, or irregular hail, we switch to vibro replacement because fine grain soil have high cohesion and low permeabilities. Their particle cannot rearrange under pure vibration. Therefore, instead of trying to compact the native soil, the probe displays it to install a matrix of dense stone column, physically reinforcing the soft ground. The underlying principle relies on creating a composite foundation support system. The resulting ground consists of a steep stone pillar boundary by intervening native soil, creating a low compressibility matrix with high load capacities. Furthermore, because these stone columns serve as high permeability matrix with high load capacity. Furthermore, because these stone columns serve as high permeability escape routes, the axis for water pressure generated by a structural loading dispatch rapidly. This means that necessary consolidation settlement occur at a dramatically accelerate rate during the construction phase itself, preventing post-construction damage. This systematic highlight the field excavation sequence, the heavy crane molded vibroprop sink deep into the soft clay layer as it encounters weak horizontal stone aggregate are introduced. Just probe is rise and lower rapidly to compact the stone aggregate laterally against the clay wall, building a dense continuous stone column from the bottom up to the surface. To warp up the technical look at vibro replacement, its core mechanism relies on a structural reinforcement and accelerate drainage. It is highly effective across challenging profile, mixed deposit of clay and sand, soft silt, ultra soft marine clay, and even loose garbage landfill. It provides excellent mitigation against liquefaction and lateral spreading. Common applications include airport, runway, bridge, abutment, railway embankment, and deep offshore structure. Its typical maximum operational depth range between 20 to 40 meters. Thank you. Thank you very much for our time and attention. I hope this detailed breakdown of dynamic compaction, a stone column, and vibro methodology provide valuable material for our classroom and research project. Thank you to everyone. Have a nice day. Thank you, sir.
Thank you so much, sir, for such
Thank
a
you, ma'am.
wonderful and enriching session.
Thank you, ma'am.
Now, as we come to the end of today's enriching session, I extend my heartfelt gratitude to our esteemed resource persons for sharing their valuable knowledge and insights. I also thank all the participants for their active participation and enthusiastic involvement throughout the day. I am just connecting with our respected director, sir, Professor Dr. Priyadarshi Jaruhar, sir.
Respected Dr. Rajendra Prasad Verma, sir, our Head of Department Civil Engineering and Associate Professor, and Dean Academics and Administration. My dear participants, the topic which was chosen is a very relevant to this FDP, and the utilization of resources is very important, particularly in today's context. The topic chosen by Dr. Verma was disaster, uh,
Ground improvement.
Ground improvement technique using waste material.
ground improvement technique using waste materials. So it is solving two-way, I think, two-way benefit. One is the waste material recycling and other things which have become a great problem for us here in India and abroad. At the same time, when we reclaim this land by this technique, it will be very much beneficial all over the India, particularly the areas which is marshy and other lands. So I appreciate this presentation very well, and
Thank
I
you, sir.
think our participants will also have good knowledge of this area. Thank you. Thank you very much.
Thank you, sir. We look forward to welcoming you again tomorrow for another day of learning and interaction. Have a wonderful evening, everyone. Thank you.
Please join by 9 a.m. 9:55 a.m. sir.
Tomorrow. I request everybody to join us again tomorrow sharp at 9:55 a.m. Thank you very much.